So let's look at what we have so far. What does the first derivative tell us? I mean, what does the original function tell us? What does it give us information-wise when it comes to curve sketching? Actually, you'd be surprised how much it gives us. What can we find by just the original function itself? The x-intercept, the domain and range, yes. The y-intercept, the domain, the range, the shape, the direction. When you say positive, what do you mean positive and negative? Yeah. Yeah, if the leading coefficient, because remember, in any polynomial, always look at the leading coefficient. That tells you the shape and the direction of the curve. What else do we need to know? There was something else I thought about when you asked that question. Um, you can't really tell that by looking at. Well, I guess you could if it has any vertical asymptotes. Continuity, horizontal asymptotes, vertical asymptotes, or oblique asymptotes. What are asymptotes? Never cross. It approaches, but never crosses. Well, the vertical asymptote never crosses. Horizontal asymptotes you can cross. For example, the last example we had here. Let's say that the x-axis was a horizontal asymptote. If your graph crosses the horizontal asymptote, it has to go back and start approaching that horizontal asymptote from the other side. A horizontal asymptote has to be approached by the graph at some point. If it crosses, then it has to start getting towards it. Let's see what else. We'll come back to that. But say that's just from the original equation. That's what we did in algebra. Now, what does the first derivative tell us? Okay, what else? Whether it's increasing or decreasing. What's that? How do you mean?
I thought you might see the slope, but if it has you can find the drift. Isn't that where you can see it's differentiable or not?
Well, if you take a derivative, it's differentiable. That's what it means. Differentiable simply means you can't take a derivative of it. It also means it's continuous. So it tells us the slope. By the slope, it tells us if it's increasing, decreasing. If the slope is positive, it's increasing. If the slope is negative, it's decreasing. But it tells us one more important thing. The vertices. Yeah, where the slope equals 0. Everything's great. Except, what about, let's say if we have the last one we had a cubic function looks like this. We can find the intercepts. That's not a problem. We can find the y-intercept. That's no problem. We can find the vertex. That's not a problem. We know where it's increasing, decreasing. But there's one more thing about the curve that we have to figure out. The shape of the curve. We know it's increasing. This is the vertex. It's a maximum because it's increasing then it's decreasing. Now this another vertex, it's decreasing, then it's increasing. But what happens in this domain between A and B? What happens to the curve there? Because think about it. If it's increasing here and decreasing here and decreasing and increasing, what happens where the two meet? Where does it stop being decreasing and starts going up to the increasing part? Think of an airplane. If an airplane goes up and starts going down, eventually the pilot has to do what with the joystick before they hit the ground? Has to pull up on the joystick before they make the airplane go up. At what point does the pilot start pulling the stick back from pushing it down to start pulling it back up? That's what we're going to look at in this section. When that happens, that point, that location is where it stops being decreasing and starts being increasing. Concavity. Concave down. That's the cup being upside down. This part is concave up. If it's concave up, we call it convex. Like a ship, a satellite dish. It's convex. But now, what happens in the middle here? At this, there's a point. It's called the point of inflection. That's where it stops being concave down and starts being concave up. At this point, it stops being down, it starts going, because if you look at it, what's happening is the rate of change decreases. Instead of going back down further, it now starts going back up. That's called the point of inflection. So let's define concavity. Definition. The graph of a differentiable function f of x is concave up on an open interval if f prime is increasing on the interval. It's concave up if it's increasing on that interval. What does that mean? If it's increasing, it's going up. Or it's concave down on the open interval if the first derivative is decreasing on that interval. And that's what we look at here. So we can't always look at just the slopes. So there's a faster way of doing this. It'll be in the lobby I'll sign it at the way out. I'll give you autographs on the way out. To, to determine concavity of a graph, we use the second derivative test for concavity. Let f of x be any twice differentiable function on an interval. Okay, this is important. We've never heard that restriction before. Let f of x be any twice differentiable, which means it has to have a second derivative. Has to be a twice differentiable function on the interval AB. A, if the second derivative is positive, then the graph of our function on that interval is concave up. If the second derivative of that function is negative, then the graph of that function on that interval is concave down. That's pretty straightforward. But same as we talked about earlier with the increasing, decreasing aspect of the first derivative, we have to have intervals, which we'll talk about next. Let's first look at an example. Example 1. Find the intervals where the functions have concavity. And here they are. Here's the first one. A. Y equals x cubed. Concavity. What do we need for concavity? We need a second derivative. So let's find the first derivative, which is 3x squared. And then the second derivative, which is 6x. So where is it concave up? Where is it concave down? So concave up when the second derivative is positive. Concave down when the second derivative is negative. Hmm? Well, no, but let's say if X, remember, we have to look at the entire domain. If I put negative numbers inside there, what is a concavity? It's negative. So it's concave down from negative infinity to zero. It's concave up from zero to positive infinity. Well, it's a cubic function. What is the graph of the cubic function? If you look at that, this is concave down. This is concave up. And you notice the point they share. What's the point they have in common? At zero. This is holding a special point. That's the point of inflection. The point of inflection is where it changes concavity up to down. And well, obviously, I'll jump to that right now. It's where it equals zero. Because this is less than zero, greater than zero. The point of inflection is where the second derivative equals zero. So 6x equals zero when x is equal to zero. So the point of inflection is at x equals zero. And that's exactly what our graph says. Okay, that was A. B is going to be x squared. B is going to be x squared. Same thing. Find the interval where the function has concavity. So we take the first derivative, we get 2x. We take the second derivative, we get 2. What do we notice about that? Well, yeah, but it's more so about constant. What do we need to know about concavity? It has a second derivative, therefore it has concavity. Is it positive or negative? It's positive, so it's everywhere concave up. So concave up from negative infinity to positive infinity. Concave down does not exist. Example 2. Determine the concavity of this function. On the interval 0 to 2 pi. So what's the first thing you got to do? What's the first derivative? Remember, for the trig functions, sine, cosine, negative cosine. This goes this way. So 3 disappears, so it's cosine. So the second derivative, the derivative of cosine is negative sine. Let's see what the graph looks like. So it's pi over 2, pi, 3 pi over 2, 2 pi. So the sine function looks like what on 0 to 2 pi? At 0, it's what? Sine at 0 is 0. Sine at pi over 2 is 1. At pi, negative. So it looks like this. But our function tells us to do what? No. Our original function, we're transforming it. Does a sign shift anywhere? No. So all it does is go up 3 spaces. So our graph, 1, 2, 3. So this is going to be my new origin. I go up 3 spaces. So my graph at pi over 2, pi, 3 pi over 2, and 2 pi will simply be shifted up. So it's here, here.
Sir, shouldn't the
Yeah.
graph be flipped for sign since it's negative sign?
What's that?
Shouldn't the graph be flipped for negative sign, or is that already negative sign?
Negative sign is a second derivative.
Yes, sir.
And we don't graph the second derivative. The second derivative is only used to find the concavity. The graph of the function is this one.
Okay.
The graph is always the original function. So we're only drawing the graph. If it has to do with points on the graph in the graph, it's always the original function. If it has to do with slope, it has to do with the first derivative. And concavity is second derivative. Concavity has nothing to do with points of a curve. It simply has to do with the shape, the bend of the curve. So what do we know about this curve now? How do we figure this stuff out? What we have to do now, this is a good place to introduce the point of inflection. Since we know we have the endpoints, the point of inflection is where the second derivative equals 0. So our second derivative is negative sine x. It equals 0 where? It equals 0 at 0. It equals 0 at pi and at 2 pi. But a point of inflection is where it changes concavity. In other words, if one side's positive, one side's negative, then the point in the middle is the point of inflection. Point of inflections never occur at endpoints. Point of inflections never occur at endpoints. So it's where the concavity changes. So the only place we're looking at, this is our point of inflection. Which means what? What's that good for? Is now, since we know this is our point of inflection, we can take a point to the left of it. Let's say pi over 2. Plug that into our equation. plug that into our equation. So what is sine of pi over 2? Sine of pi over 2 is 1, but the negative in front of it makes a negative 1. So since the second derivative at pi over 2 is negative 1, it's concave down. So we know our function is concave down from 0 to pi over to 0 to pi, it's concave down. From 0 to pi, it's concave down. Now we take it at 3 pi over 2. We do the same thing. Second derivative at 3 pi over 2, which is negative sine at 3 pi over 2. Sine at 3 pi over 2 is negative 1. So negative negative makes it a positive 1, so it's concave up. So it's concave up on the interval of pi to 2 pi. That's how we differentiate the graph itself and show what happens there. How do we find the vertices? Well, take the cosine, set it equal to 0. Cosine 0 where? At pi over 2 and 3 pi over 2. So you see what's happening here? We're slowly developing the graph, the shape of the curve. Example 3. And point of inflection of this function, x cubed minus 3x squared plus 2. Determine the concavity and the point of inflection of this function. Actually, also tell me the vertices. All right, let's look at this. To find the vertices, what do I have to do? Right, that's the first derivative. So the first derivative, 3x squared minus 6x. I can factor out a 3x, so it's x minus 2. So we have our vertices. So we have a vertex at 0, 2, 8 minus 12, negative 4, and negative 2. What do we know about the graph? What's the graph going to look like, basically? What's the shape? Anybody? Gonna be positive? That doesn't mean anything.
Um, like, second one, second three will go down.
Right. So it's a cubic function. Because it's a degree 3, that means both ends point different directions. Since it's positive, the right side points up and the left side points down. Because we have 2 vertices, that means we're going to have 3 x-intercepts. Because the number of vertices is always 1 less than the number of x-intercepts. So the graph will look something like this. We have the vertex at 0, 2, and at 2, -2. So my x-intercepts will be somewhere between there. So it has to look like this. So those are my vertices. My second derivative is 4x minus 6 for my concavity. Set that equal to 0. My point of inflection is at x equals 3/2, or 1 1/2. So my point of inflection is somewhere between 1 and 2. Concavity. Since we set it equal to 0, we know our point of inflection is 3/2. Anything to the left of it, and anything to the right of it. So if I pick a value to the left of it, of 3/2, so let's say 0. Plug it inside here. In my second derivative, I get -6, which is concave down. So the graph will look like this on this side. On this side, I pick 2. So my second derivative at 2 is 4 times 2 minus 6. It's positive, so it's concave up. It will look like this. It's just that at the point x equals 3/2, that's where the 2 join. All right, we'll stop here. I really thought we were going to get a lot further today, but there's a lot more to explain than just do these problems.